Okay, so last thing we're going to look at this week is 4.5 part 2. And we're going to look at using a formula, all right, to make a prediction. So how do you get the formula? You use the calculator. So that's what we did yesterday. Now I'm going to say, okay, you got the formula. I'll just give it to you, and I'm going to ask you to do something with it. So the two things that you can do, you don't have to write this down yet, is interpolate and extrapolate. Okay? I'll tell you what those two things mean. This last thing, that's a little different. We just have to define what those words mean at the end. So, interpolation, and you can write down on your guided notes, just the word in bold, that's all you have to write, is when you make a prediction between two values. It's when you make a prediction between two values, right? Let's say that I know if you're 30 years old at this company, you make a certain amount of money. And if you're 40 years old, you make a different amount of money. I want to predict what happens if you're 35. Well, that's in the middle. I know 30. I know if you're 40. What about if you're 35? That's interpolating. That's making a prediction between two that I know. Extrapolating is making a prediction beyond my data. So I know how much money you'll make at this company if you're 30. I know how much money you make at the company if you're 40. How much money will you make when you're 50? That's making a prediction beyond the data that I know. I only know how much money you make if you're 30 and if you're 40. I'm trying to predict beyond that. Not in between, but beyond. So interpolation, you're making a prediction between two things you know. Extrapolate, you're predicting beyond, outside your data. When you extrapolate, you have to be careful, right? Because if you try to extrapolate too far, it might not be accurate. Like if I said, all right, you make this much money when you're 20, you make this much money when you're 30, how much money would you make when you're 65? That's a big prediction because I only know how much money you make when you're 20 and you're 30. You're trying to make me predict way, way, way down. That might not be that good of a prediction, right? So you got to be careful. You don't want to try to extrapolate too far because it's not accurate. All right? So that's what I'm saying right here. And you guys have that printed. In general, if you try to make a prediction very far away from your data, it's not going to be as accurate. Okay? The further away you get from the data, the less accurate it is. Right? So if I had a bunch of points like this, and you said, make a prediction what's going to happen way over here. Maybe the data goes like that. But you're asking me to make a prediction that's way beyond the end of my data. Right? Maybe the points go like this. Maybe after a while they curve back down. I don't know. You're having me predict so far away, it might not be that accurate. All right? Versus if you had points like this, and you had a line, and you said, I want you to predict what happens between those two dots, like right in there. That's interpolating. I'm making a prediction between 2 points, not way off the end. That's extrapolating. All right, so this is a formula that you would have gotten using the calculator, practicing what we did in the warm-up. We're not going to practice it again. Okay, so you guys have that formula already printed. You just need to fill in the two arrows. So this is a formula that basically tells you how long you have to wait until the next eruption of this geyser. Right? So that's a famous geyser in a park, and it only erupts every so often. And a lot of people wait around to watch it and see when it erupts. This formula predicts how long you have to wait. Right? And it depends on two things. Well, actually, one thing. It depends on how long the eruption was. That's eruption duration. Because sometimes you watch for the geyser and it goes off for like a minute and it's done. Sometimes it goes off for like 5-6 minutes and then it's done. Right? It depends on, like, there's a lot of science the way geysers work. So X is duration, and Y is time you have to wait until the next eruption. Okay? Sometimes you have to wait like 70, 75 minutes if you miss it. You just have to stand there and wait for it to happen like an hour or so. All right. So the first question says, approximate the eruption duration. What letter in our formula is duration? X or Y? X. So approximate the duration if the time until the next one is 77 minutes. Time until eruption is 77. What letter is time until eruption? Y. So you're going to fill in the time is 77 for Y. So it's 77 equals 12.0x plus 35. And this is a prediction. Okay, we're making a prediction that if Y is 77, we're going to solve for X. This isn't a guarantee of what happens. Right? It's a prediction. Right? The geyser, it's like something in the earth. It's unpredictable. There's kind of a pattern to it, but this formula might not be perfect. We're just making a prediction. Question?
So, do you know how there's a 12.0?
Yes.
Why does the 0 have to be?
You really don't even need the 0. Usually if it was like 12.1, then we would need it. But we really could just write it as 12. If you don't want to put the 0, it's okay because it's just a 0. All right. What's the first thing we would move to the other side to solve for X?
35.
Yep. And how would you move it? Subtract. Subtract. I'm just going to go over to the right so I have enough space. What's 7 minus 5? 2. And 7 minus 3? 4. So 42 equals 12x. And what's my last step?
Divide
Yep. What do you divide by?
12.
12. 12. So if the time is 77 minutes, then the duration should be, according to this formula, about 3.5. So 3.5 equals x. Right, so that means if you waited 77 minutes for the eruption and you watch it, it'll probably last about 3.5 minutes. Is it guaranteed 3.5 minutes? No. The formula is just a prediction. It's a rough guess at what might happen. Yep. Yep. Right. Let's try it the other way. Let's say that you're waiting. There's usually hundreds of people that like to watch this because it's pretty cool if you've ever seen it. Let's say that a bunch of people are waiting, and you ask someone, well, how when the next time it's going to go off? And they say, well, the last time the duration was 5 minutes. We can figure out how much longer you have to wait to see it again. Okay? So, duration, 5 minutes. What letter here is duration? X. So we're going to fill in for X. And if we fill in a 5, it's going to tell you how many minutes you have to wait to see it again. Right? So let's fill in 5 for X. So what letter is going to be on the left? Y. What number is in front of the X? 12. And X is duration. Duration was 5. And it's plus what on the end? 35. So, what's 12 times 5? 60 plus 35. 95. So, if the last time that the geyser went off if the last time that it went off, it lasted 5 minutes, you're going to have to wait 95 minutes to see it again, right? That's what this formula is basically saying. Okay. Usually what happens is if the duration was long, like if you really go and see this geyser at Yellowstone National Park, if the last one was really, really long, you're going to have to wait a long time for the next one to happen.
Can't you just leave?
What? You can, but you might not get a spot because there's thousands of people watching it. So if you leave, someone else might take your spot. But you might be able to see it from behind a lot of people, kind of. Because it goes high. I mean, it shoots in the air like very high, 50, 60 feet. So if the previous duration was very short, like let's say the geyser erupted, went off for 10 seconds and stopped, it'll probably erupt again very soon, right? So there's only so much water. So if it uses up all the water in the geyser, it takes a while for the water to come back again and do it. Right? But that's the formula. All right, let's try one more. Okay, so example 2. This is a formula that you would have gotten using the calculator. They would have given you some data. You would have typed it in. There's your formula. So we're not going to type it in. I'm just going to tell you what it is. X is teachers and Y is students. So this formula is making a prediction based on the size of the school, how many teachers are at the school. In general, you would probably think more students at the school would have more teachers. If you have less students, you probably wouldn't need as many teachers. Right? So this formula is for a specific school. Not all schools, just one specific school that they did the formula for. So it says approximately how many students would be at a school that has 20 teachers. Right? Now, yeah. Now, remember, the formula is just a prediction. It's not a guarantee. Like, if you have 20 teachers, you have to have 500 students at a school. Maybe you have 510. Maybe you have 509. It's just a prediction. Right? So, 20 teachers. What letter would we fill in 20 for? Because it's 20 teachers. Yeah. X. 20 teachers, and what letter are you going to solve for?
Y.
You're going to solve for Y, which is how many students at the school. So the number of students equals 21 times, how many teachers are we filling in? 20 plus 42. Right. Let's type that in. So I'm going to type in 21 times 20.
400.
And what am I supposed to add to it?
42.
42. So that's about 462 students. Now remember, that's a prediction. It's like when they predict the weather and they say, oh, it's going to snow 2 to 4 inches, right? It's not exact, right? This formula is just a rough guess that if you had 20 teachers, you could have a school with about 462 students. Maybe it would be 465, maybe it'd be 468, right? That little leftover amount is called the residual, right? That's how much the prediction is off from the actual number. But that's all you do. You plug in for one letter, and you solve for the other using the equation that would come from the calculator. Any questions on that one? What letter would you plug in for if I said a school has 500 students? Predict how many teachers. What if you had 500 students?
Then you would plug it in for Y.
Then you'd plug it in for Y, and you'd solve for X. And that's what some schools do. Like if they know like a brand new school was starting, and they say, oh, we're going to have 800 students in the school. How many teachers do you think we're going to need to hire? Well, they could plug it into a formula and say, okay, we're going to need about 30 teachers.
What does the 21 stand for?
That's just the number that the graphing calculator would give you for the slope. That's all. Yep.
Wait, what's the 42?
If you really want to know what the 21 means, it means that for every 21 students you add to the school, you need one more teacher.
Well, what's the 42 for?
That's the y-intercept. They don't really explain what it would be.
Oh.
Yeah. They don't really explain it in this problem. All right, so the very last thing is not a calculation at all. Okay? It's answering question yes or no.
What about the other questions?
Yeah, we're gonna skip 2B for now.
What's for Hager?
So the 335 one, we'll skip that one.
Can I go to the bathroom?
Yeah. So on the back, on your guided notes at the top, where it says a change in one variable causes a change in the other, that is called causation. Okay? Causation means if you change one thing, another thing has to change with it. Has to. It's like directly connected. For example, let's say I looked at how many minutes I walk on a treadmill and how many calories I burn. If I change the number of minutes on the treadmill that I walk, is it going to change the number of calories I burn?
Yeah.
Yes. Yeah, assuming you don't change anything else. Don't change the speed, don't change the incline. Keep all of everything else the same. Just change the amount of time you walk. It's guaranteed. If you walk for 10 more minutes, you're going to burn more calories. That's causation. Change the time on the treadmill, you will change the amount of calories you burn. And we're going to look at a few more examples like that. All right? So causation means that there is a connection between two variables. But the flip side of that isn't always true. Just because there's a connection between two variables doesn't mean one automatically changes the other. For example, do you think there's a connection most likely between how much you study and the grade you could get on a test?
Yeah.
There could be. There could be a connection between how much you study and the grade you get. Now, if you study for an extra hour, is it an automatic guarantee your grade's going to go higher?
No.
No. It's not like a treadmill. If you walk for an extra hour, it's a guarantee you're going to burn more calories, right? But if you study an extra hour, it's not a guarantee you get a better grade automatically. Is there a connection? Probably. The more you study, the higher your grade. But it's not a guarantee, right? So causation means it's a guarantee. Correlation means it's a connection. It's not a guarantee, though. So let's look at some examples. All right. So what I want you to do here in example 3 is tell me if it's causation, which means changing one thing has to change the other, or it's just a correlation, meaning there could be a connection, but changing one thing doesn't necessarily mean the other changes. All right. Wow, we basically just did this one. Time spent exercising and the number of calories you burn, right? So the first thing is, do you think there's a connection between exercise time and calories burned?
Yeah.
So I'm going to put correlation is likely. Now, it says, if you think there's a connection, is it causal? Causal means if you change one, it has to change the other. If you change the time, is it guaranteed it's going to change how many calories you burn? Yes, it's guaranteed. If you walk for a shorter amount of time, you're going to burn less calories. So yes, there's a connection, and it is causal. Causal means you change one, it has to change the other. That's what we wrote right here. Causation. Causal. Same thing. All right. It helps. Let's look at one where it's not. So you can see it, one of those. Let's look at B. The number of banks and the population of a city. Do you think that there could be a connection between the size of a city and how many banks are in the city?
Yeah.
Yeah, there could be. Yep. Yeah. I would say if you looked at a big city like Boston, I bet there's more banks in Boston than there are banks in like Ashburn. Probably, right? So I would say that a correlation is life. Now, is it causal? If you change the number of banks in a city, like let's say you build 3 more banks, does the population of the city automatically just go up? No. If you tear a bank down, does the population of the city just go down? No. So that's not causal. Just because you change one, it doesn't necessarily change the other. Automatic. Okay, it's not automatic. So I'm just going to say not causal. Connection? Probably. Think of Boston. Big city, probably more banks than like Ashburnham. Small town, less banks. But just because you build a new bank doesn't automatically mean the population goes up. It doesn't work that way. Right? But there is probably a correlation. Right, let's look at another one. Here you just have to write yes or no. The amount of time you talk on a cell phone and the amount of battery life that's left. Do you think there's a connection?
Yes.
Yes. So that's a correlation. There's probably a connection between how long you talk and how much battery life is left. Now, is it causal? Meaning if you change one, does the other change? If you talk more time on the phone, is the battery automatically going to go down more?
Yes.
Yes. I mean, if you don't plug it in. So, what if you talk less time on the phone, is the battery automatically going to go down less?
Oh, yes.
Yes. Like if you don't use the phone as much to talk, it's not going to go down as much. If you use the phone more to talk, it's going to go down more. So that's causal. Change the amount of time you talk, you're going to change the amount of battery that's left in your phone. Guaranteed. Okay. Let's look at this one. The height of somebody, or a toddler person, you can, any way you want to read it. The height of a person and the size of their vocabulary. Do you think there's a connection between somebody that's taller and somebody that's like short, like a newborn? Could there be a connection between vocabulary?
No.
Yeah.
Yes.
Yeah, I would say there could be a connection. I mean, if you look at somebody who's 6 feet tall, and you look at somebody that's like 1.5 feet because they were, like just born.
What if they were midgets?
Right? Well, right, it's not causal. So if you look at somebody that's 6 feet tall, and you look at a newborn baby, because they're only like maybe 18 inches long, the taller person in that case is going to have a bigger vocabulary. So there could be a connection between the height of a person and a toddler's height. Definitely. There could be a connection. Now, if you change the height of a person, does it automatically change how many words they know? No, not at all. Just because you get taller doesn't automatically mean you learn more words. I mean, you probably should, right? As you go from being like 1 year old to 5 years old, you should be learning more words as you get taller. But there gets a point, like if you're already 15 or 16 and you get a little taller, you might not be learning any more new vocabulary words, unless you're actually trying to learn new words, right? But it happens kind of when you're young, it happens automatically, right? But not necessarily when you get older. Yeah? Yeah. And let's look at this one. The weight of a dog and the length of its tail. Do you think that there's a correlation between...
Yes.
No.
Yes.
Well, it depends.
I mean-
There's more if it's a puppy, it's not going to be as big as if it's like an adult.
But could you have like one breed of dog that's like really, really big dog with like a really long tail, like a golden retriever has kind of a long fluffy tail, versus like maybe there might be another kind of dog that's big but has a really short little tail.
That affects the weight.
No.
So do you think
Because there's more dog to weigh with a longer tail.
what about if it was like a different breed of dog though? It might have a shorter tail.
Yo.
Well, it's just in general. Does the weight of a dog necessarily tell you how long of a tail it's going to have.
Yeah.
No.
Oh, no, wait.
I thought it was asking if the length of the tall, like, if that affected the weight.
Or that's like saying, does the age of a person affect how long their hair is?
Yes.
Oh, that might be a better one.
Okay.
Do older people always have longer hair?
Yes.
No. So let's think of it that way.
Yes.
Okay, the age of a person doesn't necessarily affect how long their hair is. You can have old people with long hair. You can have old people with short hair. So let's think of it that way.
We have like 2 minutes left.
It's okay.
That's yours. Never mind. No.
Can I please have everyone's attention?
All right, so guys, let's just finish that up. Do you think that there's a connection between age and hair length?
Is there because you can be like my age.
Right.
Mr. Hager, is there
Yep. 1 second, guys. Just you guys, please sit down.
The library will also be closed today after school and
Okay, so last part of the question. Do you think, Steven, I still have 3 minutes. I have plenty of time. It's okay. You're still going to get to leave at 2:40. I promise. You will. I guarantee it. Unless you don't want to leave at 2:40. But I won't stop you. As somebody gets older, does their hair automatically get longer all the time?
No.
No. You might lose your hair as you get older. You might cut your hair. So just because I'm older than you doesn't mean my hair is longer than your hair. So the answer here is no. Okay, homework tonight. It's actually going to be a worksheet that reviews for the test. It's going to be a study guide. Okay? Tomorrow, in class, we will go over the study guide and any questions from last night's homework.